Today we're going to talk more about the stoichiometric matrix. Last time we were introduced to it and its various attributes, and experience shows that it is very informative about physiological states, and therefore there is great interest in studying its deeper mathematical properties. So this lecture will focus on that subject. It's a shorter lecture, but it is probably the most mathematically dense part of these lectures. So here's the outline of what we're going to talk about. We're going to talk about singular value decomposition. This is the most fundamental way to break a matrix apart and figure out what it tells you. You can do this for any matrix that you have. But of course here we're going to be looking at singular value decomposition of the stoichiometric matrix to get at some of its fundamental properties. So the first part of this lecture is going to be more on mathematics and what SVD is, and then the second half of the lecture is going to be focused on applying it to stoichiometric matrices and see what we can learn. There's a little subject at the end that speaks to rotating basis vectors. We're going to talk a lot about orthonormal basis vectors in this lecture, but they may not be the most biologically meaningful ones, but there's a simple trick that you can use to rotate them to make them more chemically pristine. All right, so singular value decomposition and its uses. So again, this is the most fundamental way of looking at the matrix and decomposing it into its parts. If you've had a class on linear algebra, it's normally covered at the very end. Sometimes instructors run out of time and don't do it justice, but it is, the most fundamental way in which you can view a matrix. Okay, so what is singular value decomposition? So last time we talked about the fact that the stoichiometric matrix basically takes the flux vector that we denote by a lowercase v, boldface, and it maps it into a vector of derivatives of the concentrations. That's what it does. And what's written there in the middle is the singular value decomposition of S. It's written as a product of three different matrices, U, sigma, and V transposed. And it's uppercase V, and it's a matrix. Slight overlap here in nomenclature between this matrix V and the vector, the reaction vector, or the flux vector, lowercase v. So we're going to get introduced to these three matrices and what they say. So to the right is the dynamic mass balance equation that we talked about last time that describes the dynamic and steady states of a network. And we can substitute for S in this equation that product of three matrices. And we'll be playing a little bit with that in this lecture. So since S is a mapping of V into X dot, or the derivative vector, and S is factored into three matrices, you basically take that single mapping and break it down into three separate mappings. First, V transposed, and V is called the right hand, it's comprised of the right-hand side singular vectors. And you get something, and then you map it with sigma, which, as we'll see, is a diagonal matrix, and that results in another vector that is then mapped by U, which is comprised of left hand side or left singular vectors back into the time derivative vector. So I'm going to take S and break it into three different mappings, and that is shown pictorially here. At the top of this diagram, V is just mapped straight into X dot, or we can go through these three mappings that are shown at the bottom. And since V is a vector, and if I multiply it by a matrix, every row in that matrix V transposed times V will give me a linear combination of the fluxes as specified by the elements of that row. So what I get by mapping of V transposed is a linear combination of fluxes, and many different linear combinations of fluxes, where each combination is in each row in that column vector. Then sigma, it's a diagonal matrix, so it stretches these linear combinations of fluxes. That's what it does, and it acts only on one at a time because it's diagonal, so it's a decoupled operation. It just maps, it just multiplies basically one of these linear combinations. And from that, you get something we'll talk about a little bit more in a moment, but you get linear combinations of the concentration derivatives, and then U reassembles those into the individual concentration time derivatives. So this is a way to decompose S into these three separate operations. So we're gonna, in the first half of the lecture, talk a little bit about the mathematics behind this and how this is useful for us. But first, let me try to give you a feeling for what singular value decomposition actually does. It's heavily used to manipulate many different types of matrices. And a photograph is a matrix. If it's pixelated, it's a matrix. And if it's black and white, it's just a single matrix with the numbers of a gray shade scale in each dot. If it's three colors, it's actually three matrices for each one of the fundamental colors. So here's a picture of a ballerina dancing. And this image is a matrix with a rank of 303. So 303 rows in this matrix are independent. So there are 303 independent pieces of information in that matrix. Okay? And they all together, when put together, give you that image of this dancing ballerina. Now the singular value decomposition is going to parse S into R different matrices. One matrix for every independent piece of information, and it's going to rank order them in terms of their contribution to the matrix, and we'll see this mathematically in a moment. And it turns out that often very few of these matrices give you most of the information in the original matrix. And for instance, this image here is comprised of the pieces of information in the image associated with just 5 of these 103 independent pieces of information. These 5 obviously are the most important ones because they reconstruct most of the image. You see it's a ballerina, she's dancing, you may not see a necklace or something like that, or what kind of shoes she's wearing, but you basically see the image. And if you call out more pieces of information, here's 5 more of them, and you see the resolution of the image increases. And I can call out 30, 50, and eventually all the 303. And if I call out all the 303 pieces of information, I have a full reconstruction of the matrix, and I recover the entire image and all of its detail. Now, why is this important? Let's assume that you're driving a rover on Mars that's snapping photos, and you have a very limited bandwidth to send information back to Earth. So what you can do in the rover is you snap an image and you can decompose it. And you can just start sending it mode by mode. And you may be satisfied in this case with 30 of the modes, and you don't want the other, whatever, 273, and say, it's fine, let's go on to the next image. So because most of the information you want from that image has already been sent to you at 10% of the bandwidth of the channel you're using. So that's one example of how we use SVD. So SVD is used for image processing. It's used for noise reduction, to get a signal out of noise. And you try to get the dominant features of a signal and eliminate the noise. It's used for engineering applications and kinematics. And it's also been used to extract information for expression profiles. And this application here at the end is most relevant to us, so maybe I'll talk a little bit more about that. These, what's shown in the matrix in that block to the right, the green and red matrix, is expression profiling of yeast, all 6,000 genes, over something like 18 time points in a cell cycle in a synchronized culture. And so this is a huge matrix, let's say roughly 20 by 6,000, so you can multiply what that is, 120,000 data points or so. But you can do a singular value of that matrix. You see kind of structure to it. And if you do that singular value decomposition, you find out that there are really only 2 independent modes in this matrix. And most of the other, so out of 18 data sets, they really map onto 2 informative dimensions. And those are shown pictorially to the furthest right in that image. And you can see that there are 2 distinct sets of genes that are oscillating throughout the cell cycle as shown over there. This is also a statement of what I think I mentioned before, the fact that omics data set, although they have a lot of data points in them, are of low dimension because there's such dependency amongst the variables that we are measuring. So those are some applications of singular value decomposition. So this is why we'd like to use it. So let's talk about some of the basic mathematical features here. So there's our dynamic mass balance to the top left. Substitute that matrix in there. And by doing that, I can study these 3 separate transformations that I outlined before. And we're going to talk about each one of them now and what they actually do and what the information content of these 3 matrices is. I just want to mention that when you write code, you should always be doing quality controls and numerical checks. And in that top box to the left is the MATLAB command for doing SVD. So you can just do SVD of S and you get back these 3 matrices shown there. And what you should always be doing is to check the accuracy of such calculations. So if you take the norm of S minus what the program gives you back, the norm of that matrix that you should get should be at or below the machine accuracy. If that's not the case, the computations were done incorrectly. And I just say this because some years ago, MATLAB could not really decompose very large sparse matrices like S accurately. Presumably today the algorithms are better, but that version of MATLAB failed that test at that time. So we put them into Mathematica and we got the pristine matrix back. So that was one of the reasons why we switched to Mathematica, because it, at least early on, seemed to have better numerics. I made no comment about what would happen with today's versions of these programs. So when you're doing calculations, this is kind of like an experimentalist doing controls. You always have to be doing controls and checking and making sure everything is okay. And that's a simple, kind of an obvious check to do. All right, so let's look at these matrices a little bit more. And I want to start out with sigma. That's the simplest one. So sigma is a diagonal matrix, and it'll have R sigma values on the diagonals, which is the rank of the matrix. And there's nothing past R. If you look in on the diagonal in the R plus 1, R plus 1 position in the matrix, you'll see a 0, and on all the diagonal elements after that. So there are a few things we can do with these numbers. So it's just a column of numbers you get. They are rank ordered from the largest sigma value to the smallest sigma value. Often we simply plot them like this, and this is called the singular value spectrum. And there are 2 spectra shown there. The one with the open circles is the more typical one, where the numerical values of sigma are going to be decaying quickly with subsequent modes. And this means that there are few pieces of information in that matrix that are dominant and represent most of its features. In contrast, the singular value spectrum denoted with the open squares is different. It's a very flat singular value spectrum, which says that every mode in that matrix is roughly of equal information. And for instance, if you were to do a singular value decomposition of the identity matrix, you will only get sigma values of 1, because the identity matrix is independent in all directions with completely equal information on each axis. That's rare, but it does happen. Now, often this spectra is normalized, so you sum up all the singular values and use that as a denominator for all of the other ones, so you get fractional singular values, as shown there, and that's often denoted by lowercase f. So if F1 is, say, 0.5, it would represent half of the singular value spectrum. So it's often useful to normalize it like that, to look at them. What is also often done is you integrate that over the index or calculate the cumulative value. So you just form the summation of these f sub i's up to I. So you just keep adding them over the index I. And of course, if you were to reach the rank R and you sum everything up, that the capital F sub R would be 1 because you summed up all the singular values, all the fractions, and they should add up to 1. Now, if I do that to this singular value spectra shown there in the graph to the top right, I get what's on the bottom right, a curve that goes up. And you see with the open circles, you will see that sum going up very quickly and then asymptotically go to 1. And if I state that criteria where it says I want to only capture 95% of the singular value because the rest of it is going to be noise or not of importance to me, I can cut the singular value spectra off at that point in time. And I think in this slide here, it would be at 4 singular values, even if there are many, many more there, because the first 4 will give me the bulk of the information in the matrix. This was true for the ballerina picture. Probably the first 10, 20 was enough out of the 303 to get what I wanted. So sometimes you do this, you cut it off there. This is often done with data analysis, image processing like I showed you. But in the case of the stoichiometric matrix, it's pristine, it's a perfect matrix. In principle, every mode in that matrix has some information. But it still has dominant features, as we'll see later in the lecture. In contrast, if I were to compute the cumulative singular value spectra for the open square situation, they would be almost linear. It would just be going linearly to 1 because every addition to that sum takes that spectra up, that cumulative spectra up by about the same amount because there is the same amount of information in every mode. So this is what's contained in the singular value, in the matrix of singular value, sigma. It rank orders how important these independent pieces of information are in that matrix. So let's look at the other two matrices, U and V, or V transposed. So just to remind you, the reaction rate vector, or the flux vector, lives in an n-dimensional space because there are n fluxes, and that space is decomposed into 2 orthogonal spaces, the row space and the null space. And we talked a little bit about those last time. So the dimension of the row space is R, it's the same as the rank, which means that the dimension of the null space is n minus R. So these are pretty important dimensions to keep track of. S will map that vector of fluxes into that derivative vector, which is m-dimensional because there are m concentrations. Now, the vector x dot is m-dimensional, and it lives in 2 orthogonal subspaces. One is the column space, and the other is the left null space. The column space is also dimension R, like the row space. They have the same dimension as the rank. This means that the left null space will be m minus R in its dimension. Okay, so these are important. Now it turns out that the matrices U and V, or V transpose as it's shown there, give us a set of orthonormal basis vectors for these spaces. So the first R columns of the matrix U give us an orthonormal set of basis vectors for the column space. So the rest of them, m minus R, is similarly a set of orthonormal basis vectors for the left null space. And V transposed does the same thing for that m-dimensional space. The first R rows, after I transpose it, have a orthonormal basis vector for the row space, and the remaining set of rows in V transposed, the n minus R rows, give me an orthonormal set of basis vectors for the null space. And as you know, the orthonormal basis vectors are kind of the nicest vectors to use for a space. You know, the XYZ coordinates we always use in calculus are orthonormal, and we span them with unit vectors ij and k, which they're normally called. So this is similar. It does the same thing. And these are going to be orthonormal matrices, which means that the length of these, every one of these basis vectors is 1. So this is a very fundamental decomposition of a matrix. It tells us basically everything that we really need to know about the matrix. Okay, so that's what is in these three matrices, U, sigma, and V transposed. And yeah, so let's talk about a couple of key mathematical properties of the singular value decomposition. There are many, but there are many properties, but there are two of particular importance here. So the first one I want to go through shows you the explicit mode-by-mode reconstruction of a matrix. And that is shown by that equation over there. So what we do here is we show that the sigma, that the matrix S is a summation of R matrices. And each one of those matrices is the singular value, the corresponding singular value, and then the outer product of the left and the right-hand singular vector. Now, you may not see outer products of vectors every day, but there they are shown pictorially. So we are taking a column vector of n by 1 and a row vector, post-multiplying that column vector by a row vector that's 1 by n. And you do that for every term in that summation. And that matrix that comes from that outer product is then multiplied by sigma, and they're all summed up. And then you get your original matrix. So you carry out each one of these outer products, you will get a series of matrices like shown there. Each one of them is going to be of rank 1, because they're just made from a single vector, basically. And they will also have a norm that's on the order of unity, because the length of U, the vectors U sub I and V sub I, is on the order of unity. So each one of those matrices have a norm of about unity. This means that in the summation, we are adding up matrices that are all of size 1, if you will, on the order of unity, and we are multiplying them by the sigma factors that now become scaling factors. So if sigma 1 is the biggest, let's say it's 100, that first term in that series will be of magnitude 100. And if sigma 2 is, say, 10, that means that the next term in there will be of order of 10. If the third sigma factor is 1, the third term will be on the order of 1. So you immediately see how much each one of these terms in that summation contribute to the reconstruction of the original matrix. So in, say, that ballerina picture, I take the first 10, 20 matrices like that, and I basically have the final matrix. If I keep adding the terms, it's just a little bit that I add to the matrix with every successive term in the summation. So this is here just to remind you what definition of orthonormality is. So orthonormality means that the length of the vectors in the matrix is 1, either the row or the column vectors, as it turns out. And if I take the inner product between these two vectors, I will always get 0 because they are orthogonal to one another. Except when I take the inner product of the vector with itself, I get 1 because that's basically its length or its norm. So that's the definition of orthonormality. Very, very useful property when it comes to numerical analysis. So that's basically how a matrix is reconstructed in a mode-by-mode fashion. And that reconstruction keeps adding terms that become less and less important because you rank order the sigma values in the matrix capital sigma. The second property that's of importance here is that if I apply S to the singular vector, the right singular vector I actually get the left singular vector I scaled by sigma. So and that's that stretching mapping by sigma that I mentioned earlier. So let's see how that goes. So here is a little bit of mathematics. on top, I have S equal to U sigma V transposed. Now I want to multiply that matrix equation from the right with the matrix V. And that's what's shown in the row below. V transpose by V is going to be the identity matrix because these are orthonormal matrices. So that disappears, and I get the third row in here, in this block of equations. Now I can look at this more carefully, and I realize that V and U are just a set of row vectors, and sigma is diagonal. So I can actually parse this equation out. I can take any column in V and any column in U and pick out the corresponding diagonal element in S, and I get that equation below. So basically, if I multiply S by any one of the vectors in V, I get the corresponding vector in U, column vector in U, times sigma. So that's kind of pictorially shown at the bottom. A matrix times a column vector becomes a scalar times a column vector. So if I take these right-hand singular values and let S act on them, I get the left-hand singular vector times the corresponding singular value. So this is a decomposition of the matrix, and that is shown there just as a mapping. So S will map Vk into Uk times sigma k. And we'll talk a little bit more about this on the next slide, what this means for us. A little bit more about orthogonality shown up there. So U transpose times U will be the identity matrix, but there's an M by M identity matrix. I do the same thing with V. I also get an identity matrix, but it's N by N. It's a very common mistake to make that mistake with identity matrices. You think they're all just one, but they are an identity matrix in a space of a particular dimension. So be careful with that if you ever do such multiplications. So these multiplications are shown pictorially down there. We have a bunch of rows multiplying a bunch of columns, and you get the identity matrix. And at the bottom of that block says that U transpose is equal to U inverse, and that's obvious from the equations above. Because if I multiply a matrix by its inverse, I get identity. And this is one reason why orthonormal matrices are so useful. They're so handy. You never have to invert them. You just transpose them, and you have the inverse. Okay, now let's talk a little bit about this property some more. And I want to look at the second transformation in this diagram showing the three transformations. And this corresponds to a differential equation that looks like this. I've already taken U transposed and multiplied into, well, I've taken let's take the right-hand side first. I've taken V transpose times V to form some linear combinations of the fluxes. And I apply sigma to that. And what I get in the derivative is going to be U transpose times X. So I basically, okay. So this equation just comes by multiplying the original dynamic mass balances by U transposed from the right, from the left, and that's what you get. So I basically map a linear combination of fluxes into a linear combination of concentrations. And that linear combination of concentrations is going to move as an independent block in response to that linear combination of fluxes. And we'll see more about this in a moment. And this set of equations looks like what's shown pictorially in the to the right, and the diagonal matrix is there. And this means that this can be written out as a set of R independent differential equations. So this means decoupling the motions from each other. Okay, and we may talk more about this later on, but this is why this second property is important. It's a way to parse out the matrix and move around the directions in these two spaces. And it's only important for the row and the column space, by the way, because there are no singular values that correspond to the null spaces. Okay, so these are the properties, mathematical properties of the singular value decomposition. This may remind you of a few lectures and homeworks that you did before. if you took a complete set on linear algebra. If not, this may all be new to you, and you may have to read this a few times to grasp these concepts, but they're very important. And not just for the stoichiometric matrix, but for any matrix you may have to deal with. So let's see now what this decomposition does for us to understand the properties of biochemical reaction networks. And I'm going to go through a couple of very simple examples that help understand this conceptually. So I'm going to start with the simplest situation of all. We have a reversible linear reaction where x1 is being turned to x2. There's a forward rate and a reverse rate. And the stoichiometric matrix is shown there. So the first column is the reaction vector for the forward reaction. The second column vector in there is the reaction vector for the reverse reaction. And the two rows, of course, correspond to x1 and x2. You look at that matrix and you can immediately see it's rank deficient. You just add up the rows and you get 0, or add up the columns and you get 0. So the rank of this matrix is 1. So then I can calculate dimensions of all the spaces associated with it. Since the rank is 1, the column space will be one-dimensional, the row space will be one-dimensional. The null space will be n, which is 2, minus r, the rank, which is 1, and that's also one-dimensional. I can also calculate the dimension of the left null space, and that's also 1. So in this case, all the 4 fundamental subspaces have dimension 1. And what's shown to the right of that are the basis vectors for each one of these spaces. These basis vectors are divided by square root of 2, which is simply normalizing it to their length. So that makes them of unit length. So that makes them proper normalized basis vectors for these spaces. Okay, now let's look at this mapping pictorially. So going from a space that is two-dimensional, comprised of V1 and V2 on the axes, and I map it into the space of the two derivatives of x1 and x2. So that's going to be what's on the axis of these two spaces. In the space where the reaction vector is, or the flux vector is, I've shown the row space vector that has that direction of 1, minus 1, and I've shown the null space vector of 1, 1, which is the correct form, not like the mistake that I pointed out earlier in the upper right-hand corner of the slide. So all the null space vectors, all the equilibria states in this system, where nothing is changing with time, will lie on that diagonal line, because that's where V1 and V2 are equal. If they're equal, the forward and the reverse rate are identical, and nothing is happening. And if I take any point on that line, which is now the null space, and shown by that red triangle, it gets mapped into 0 on the other side, because both the time derivatives will be 0. So all the steady states for this system are on that line. In this case, it's a closed system, so the steady state here corresponds to the equilibrium. Now, if I'm off that diagonal line, there will be a component in the row space. And let's say we take, for instance, this circle there, the green circle. I'm above the diagonal line, which means that the flux V2, the reverse flux, is greater than the forward flux, V1. So the net reaction is going to be from x2 to x1. And I map that now onto the column space that is shown by, I guess, a minus 45-degree line. And it will map to the second quadrant of that plane. Is that the second quadrant? Yeah. That's called the second quadrant, yeah. Where the time derivative for x1 is positive, the time derivative for x2 is negative. So x2 is going down and x1 is going up, because there's the reverse reaction. But they are on that minus 45-degree line because they're exactly equal and opposite. Because every time a molecule of x2 disappears, immediately x1 appears. So that's why all the motion in this system has to be along that line. It's constrained to that line. Orthogonal to that is the left null space of 1, 1, which we will talk about in a moment, but that is a constraint, and it basically says that x1 plus x2 is a constant, is a time invariant. So the whole motion here along the column space is constrained by the fact that the total mass is a constant. So if x1 goes down, x2 has to go up immediately. And that's what's shown by that circle that's kind of in a light blue color. So that's what these basis vectors mean. Now, let me talk a little bit more about these spaces. So, we talked about the fact earlier that the elementary fluxes are non-negative. They can't be negative. They can only be 0 or positive because they're elementary reactions. They will also have a Vmax. They can only proceed at a certain maximum rate. So when we map out of this space containing the flux vector, we cannot just pick any point in that space. There is only a segment of that plane that is meaningful to us. And it's going to be bounded. And that has a big effect on analyzing the way we analyze the state of reaction networks. And that bounded space is shown by that reddish square. So I've shown the mapping here in a little more detail now. You can see that the row space is going to be bounded by if you map the corner points of that space onto the row space, you get that open triangle and that open square. And they will map into the column space and give us the extremities of the column space. So there are maximum values of these time derivatives that can take place. We have to be on a line segment in that case. And if you look at the solid square that is in the red box there, you can break it down into the part that's in the null space and the part that's in the row space. And as we talked about before, the row space has drivers for change in it. And what's going to happen here is that solid black square is going to move along that vector in the row space and into the solid circle where it will stop. And that corresponds to the derivative getting smaller and smaller and smaller and going into the origin. Okay. So just a little more detail on how this works. And the very important point that we have bounded spaces. And as we'll see in the next lecture, this takes us from linear algebra into what's called convex analysis, because we're now going to be dealing with polytopes basically, and not spaces that are infinite in all directions, like linear spaces are. Okay, so let's do another simple example, and let's take the other prototypical elementary reaction that we deal with, where x1 and x2 react, basically combine to form an x3. So this is a little more complicated, and here is the stoichiometric matrix that corresponds to that. We have the forward and the reverse reaction vectors. Now 2 columns in the stoichiometric matrix, 3 rows corresponding to the compounds. You can see immediately that the sum of the columns is sums up to 0, so the rank of this matrix is 1. So here the null spaces, here the spaces are slightly different than before. The column and the row space will both have dimension 1 because that's the rank. The null space here also is one-dimensional. So n being 2 here minus the rank, which is 1, that gives me 1. But here the left null space becomes 2-dimensional. So there are 2 time invariants in here. And they are shown here at the bottom just by writing that reaction equation a little differently. Let's say I have a molecule C and a molecule P combining into a new molecule, and nothing, and this is in a closed system, nothing is coming, nothing is going. That moiety C is going to be conserved. It's always going to be either free or bound. And same thing with P. So there will be 2 conservation moieties in the system. And they are very easily seen by adding up the differential equations that correspond to 1 and 3. That's adding up the first and the third row in that matrix, 0. So that means that x1 plus x3 is 0. And the same holds true for adding up this, the derivative, the dynamic mass balance for x2 and x3, you get 0, which means that the summation of x2 and x3 is 0. So this hopefully gives you a little more sense for what conservation moieties are. This is just mathematically how you derive them, but you can also just chemically interpret them like the chemical equation shows. So in this case, we have a slightly different situation. we have now we have the space n by m is 3 by 3, and this is where the time derivative vector will be, and the two conservation vectors. And the two conservation vectors will form that plane that is shown in blue there, and the reaction vector will move exactly orthogonal to that. So you don't move around in the blue plane as the motion is taking place. So you stay there. Wherever you fix that point, you move above it. So if you do the singular value decomposition here, by any program you choose, you get this matrix that is shown there. That's the matrix U. And the first column has to be scaled by the square root of 3 because it's length, but I just factor that out so you can see it more clearly. It's -1, -1, and 1. It's basically the reaction vector. There's only one independent column in S, and that's what is going to span the column space for me. There's only one of them. The left null space is shown there too. It's a little more interesting. Let's look at the second one. The second column in this matrix has 0, 1, 1. So it says 1 on x2 and 1 on x3. This actually directly represents one of our time invariants. And it needs to be scaled by 1 over the square root of 2 to become, unit length. Look at the last one. That is 2, -1, and 1. It's in that plane and orthogonal to the second column. But that doesn't have a chemical interpretation like the other one. Now you can add these two columns, blue columns, up in your mind, and the element in the second row will disappear, and you will get 2, 0, and 2. If I normalize that vector just to 1, 0, and 1, I have the other time invariant. So the two spaces, the two dimensions that you get in the left null space from SVD are partially chemically meaningful. They are mathematically proper, but they may not be representing the chemistry we like. And this opens up this topic that's going to become important to us, namely that the orthonormal vectors you get from SVD may not be the best way to span these spaces in a biologically meaningful terms. So here I have changed the basis vectors for that blue plane to be the two vectors that I had before, the two vectors that correspond to the conservation moieties. And it actually turns out that since x1 and x2 are also non-negative variables, the only interesting part of that plane chemically is that hatched region. That's where the concentrations will be positive. And we'll talk more about that later. But here's a bounded space again. The left null space is bounded. There's only a part of it of interest to us. And the same thing will actually be true for the null space as well. There's a bounded part of it of interest to us. Okay. All right. So in this case, if I take these vectors, L1 and L2, that will be spanning the left null space, I will get my two conservation moieties that I mentioned. And they are not orthogonal. So L1 times L2 is not 0. The inner product of those two is not 0. So they are oblique. And they are something we are going to be introduced to in more detail in the next lecture. They are convex basis vectors. They will span that segment of the space for us where all the non-negative concentrations will lie. And this is the part of that space that's of interest to us. All right, so we can actually convert an orthonormal set of basis vectors into a convex set of basis vectors to span a part of that space that's chemically meaningful and in chemically accurate terms. And we will see more of that in the next lecture. Okay, so I think these two trivially simple examples show you that the singular value decomposition is very valuable. It takes the stoichiometric matrix and it gives you a basis for its fundamental subspaces and helps you interpret the contents of those subspaces. And we are very interested in those contents. For this class, we are especially interested in the null space itself because that's where all the steady state flux distributions lie. Okay. All right. So here I am showing the singular value decomposition of S again, where you have in the original matrix reactions and metabolites forming the columns and the rows. And then we had the matrices, the three matrices we just talked about, and shaded out the regions in them that correspond to the spanning of the column and the row space. Now, I want to introduce you now to the notion of an eigenreaction and what we call eigenconnectivity, which is going to be related to the connections in a network or the fluxes themselves, the reactions themselves. These are properties of the stoichiometric matrix. These may not be chemical properties, but they are properties of the stoichiometric matrix that come out of this decomposition. So we're going to interpret the columns here as reactions, as eigenreactions, mathematical property, and the rows in V transposed as these eigenconnectivities or combination of the links in the map. So let's talk a little bit more about that. Here's the dynamic, here's the differential equation that I talked about earlier that derives from the second property. And there will be R independent such equations. And I just want to look at it a little bit. So there are flux drivers in there, which are on the right-hand side. There's some combination of the fluxes that you're going to drive motion along that dimension in the space. And that's what's shown at the bottom there. I take one row in B transpose times the column vector, and I get that summation. I get all my fluxes times some weight. So it's just some linear combination of the fluxes. And likewise, in the derivative, I transpose U now, so the columns in U are now rows, and I multiply that into X, the vector of concentrations, and I get some linear combination of the concentration. So what this says is some linear combination of the fluxes are driving some linear combination of concentrations. And this driver and this motion is independent of everything else that happens. And is characterized by the sigma corresponding singular value, sigma k. Now I can show this in a space. So let's first think about the drivers. So there will be positive and negative elements in that sum. So some fluxes will tend to drive something forward, and there are other fluxes in that sum that tends to drive things in the reverse direction. So we can represent that in these two dimensions. We can map that singular vector into two dimensions where I put all the positive and the negative elements in that summation, and I just form that vector in that second quadrant. I can do exactly the same thing with the linear concentration of the concentrations. So some will be going down during that motion, some will be going up. And this actually corresponds to a very abstract reaction. It's not a proper chemical reaction, but it is like a reaction. So the drivers, the V's that come up with a negative value in the summation, are like driving that eigenreaction in the reverse direction. And all of the weights that are positive in there would be represent fluxes that tend to drive that motion forward. So that eigenvector has positive and negative drivers. And the motion is going to have to be along that vector. Some of these things are going up, some of the things are going down. And conversely, the same thing is going to be true for the concentrations. There are concentrations that are going to be increasing in value in that summation as you drive forward, and those that are going to be decreasing in value when that thing goes forward. So this looks just like a chemical reaction. There are forward fluxes and reverse fluxes added up in some odd way, depending on the matrix combination, that drives some concentrations down and some concentrations up. And this represents these right and left singular vectors in the column and the row space. All right. All right, so that's just what it means. But like I introduced to you before, these may not be chemically proper reactions. So later we may want to test these a little bit to make them stoichiometrically accurate. But to a first approximation, you can use these to characterize the dominant features of a matrix. So we're going to be working with the core metabolic network in E. coli that you've been introduced to in here from time to time. So this slide here shows the singular value spectrum for that matrix without the biomass reaction and with the biomass reaction. So one is just the network itself, the other one is the network plus that functionality of synthesizing biomass. So the dashed line there shows the spectrum without the biomass reaction. The solid reddish line shows the singular value spectrum with the biomass reaction in there. And you see there's this huge singular value that shows up when I add the biomass reaction that gives a dominant feature now to the network. It's about half the spectrum. So these are the cumulative spectra that I show, and then I show the individual ones down in those insets there. And it's hard to see the top one of these inserts has 1 point high on the y-axis, which is that large singular value. Everything else is small. And in fact, when you sum up everything else is small, it's about the same magnitude. So that's why the cumulative spectrum starts at a half, because that first singular value is more than a half. Now I can now look at these eigenreactions that we talked about. And here they are. So this is without the biomass, and the top panel there shows the first mode. So all the compounds that participate in that mode are shown on the x-axis in there. And I know you can't read this. There are like 72 compounds, I think, in this model, and they're shown there individually. And this bar chart shows the loading in that corresponding left eigenvector on those concentrations. And you see there are really only 2 bars on there. And the color-coded one is positive and one is negative. So I just flip the negative ones to be positive to show the relative magnitude. These 2 things correspond to the proton inside and outside the membrane. So the most dominant feature of this network is proton translocation. You see the bars aren't the same, so this is not stoichiometrically balanced, but it's telling you that this motion in the system, translocation, is the dominant feature of this matrix. And if you were able to read that systemic reaction there on top, you would see the things that drive the proton. There are various pumps in the ETS that pump the proton out, and the proton is let back in predominantly by the ATP synthase and ABC transporters. Those are the major consumers of the external proton and use it. So that's the dominant motion in here, is the translocation of a proton. If you look at the second one, you can look through that spectrum there. This is mostly associated, the second mode is mostly associated with ATP synthesis, and the forward drivers now will be the ATP synthase, some of the kinases in glycolysis that are associated with substrate level phosphorylation, and then the reactions driving it in the reverse are some of the main users of ATP. And you can go down the list. The third mode focuses on the transhydrogenase that moves redox potential from NADPH to NADH, and it couples actually with acetylation, the formation of acetyl-CoA, the use of acetyl-CoA. And since the vectors are orthogonal, now all of a sudden 2 chemical functions, metabolic functions, become intermingled in that mode. If you could rotate these vectors a little bit, you can break that apart into individual chemical motions. So we'll talk about that in a moment. But this is what you can learn by just looking at the loadings of these left and right singular vectors, because you can see what the dominant motions are in terms of the concentrations going up and down, and in terms of the basic drivers behind them. Now, if I redo this for the second case, where I put the biomass in there, I now have one dominant feature of the matrix, and not surprisingly, that turns out to be the biomass reaction that is draining mostly ATP, driving itself forward. And this will represent growth. So as soon as you put the biomass function into a stoichiometric matrix, it becomes a dominant feature of the network. So whether you're driving a network based on optimizing biomass or not has a huge impact on the properties of the network. And then if you go look at this, the subsequent modes, which are now much smaller in the sum, but they are driving the same processes. You see the translocation of the proton, you see transhydrogenation, and you see acetyl-CoA being charged and discharged. But now it's a little more scrambled up because it's a little harder to get them disentangled and perfectly orthogonal to that biomass reaction. So that's what you can learn by doing a singular value decomposition of a stoichiometric matrix. So that is satisfying because it gives you the overall features of your network. But it's dissatisfying in the sense that it's not chemically accurate. It gives you a network property, but it's not consistent with the chemistry. So we can actually get at representing the chemistry accurately in a couple of different ways. One are the convex set of basis vectors that I'm going to talk about later on. And related to it, and maybe identical to it, is tilting or rotating basis vectors. So let's take a look at this image over here. In gray, I show three orthonormal basis vectors derived, say, from singular value decomposition. I can rotate them and still span the whole space. You know, I can always rotate a base set of basis vectors. I can rotate it, and I can rotate them so they click onto stoichiometry. They're consistent with stoichiometry. So I can just rotate them and now get a basis that may represent reactions and pathways directly. So you can actually get basis vectors that represent pathways. And that's going to be in the flux space, and in the concentration space you can get basis vectors that correspond to pools. Okay, so that's just by taking, these are high dimensional spaces, and you saw very often very few of the loadings are significant. You can rotate them slightly to get rid of these small loadings that are in these basis vectors. And when you rotate the basis vector, there is no loss in anything. You're just spanning the space a little differently. I can pick an X, Y, and Z coordinate system for this room that looks like this, and I can rotate it like this, and it's still a set of basis vectors for the space. So I can always rotate a basis and get a new basis for it. So you can actually go into MATLAB, and I think the same thing must be possible in Mathematica, is that you can rotate the basis vectors based on various considerations and get a new set of basis vectors that would be more interesting to deal with from a chemical standpoint. And basically what happens is you take a matrix like this may be the U matrix or the V matrix that you have, and it's gray scaled, so there are very few really dark dots in there, a lot of kind of gray dots, a few white ones, absolutely zeros. If you rotate it, you get rid of all that noise in there, and you just rotate it so there are a few dominant elements, and ideally they would be integers or some numbers consistent with the chemistry that you're trying to represent. So to do this, there are basis rotation methods. There are two categories. You can rotate while keeping the basis orthogonal. So you just rotate the whole basis, and the angles between the vectors is still 90 degrees, and you just rotate the basis a little bit. You can also do oblique rotations that give you a little more slack. And now the basis vectors won't be orthogonal anymore, but they may rotate more easily onto a base set of basis vectors that you think represents, pathways, pools, concentrations, and so forth in a biologically more meaningful way. And in MATLAB, this is just a command that I think it looks like this. You rotate one matrix of basis vectors onto another, and you can pick which method you use to do that, and they fall into these overall categories. All right, so that brings us to the end of the lecture. Go through a few summary bullet points here. So the singular value decomposition that takes any matrix, in our case S, breaks it into these three matrices with the properties that I mentioned, is the most fundamental decomposition of a matrix. It basically teaches you everything there is to know about that linear transformation. Sigma is a diagonal matrix, and it has the singular values, and that can be used to determine the effective dimensionality of a mapping. Early on in the lecture, I used a 95% cutoff on the cumulative singular value spectrum, and I got an effective dimension of 4, even if the full dimension may have been much bigger. So it can help you assess what is the real dimensionality of a mapping. U and V transposed give us orthonormal basis vectors for the 4 subspaces associated with a matrix. Very convenient set of basis vectors. They're orthonormal, unit length, and independent of one another, and that may help us break a mapping apart. And that was indicated by the fact that you can take a right-hand singular vector and map it on a left-hand singular vector independently. And the orthogonality of these basis vectors is mathematically satisfying and certainly very useful from a numerics standpoint, but they may not be useful from a biological standpoint and an interpretation standpoint of chemical properties and biological properties. And we will next time talk about such set of basis vectors and how to deal with them. So that's the end of this lecture. It is, like I said, probably the most mathematically dense lecture in the series of lectures. But if you have had a class in linear algebra, it should not be that difficult to navigate.